So today we're going to start a module on sea level. And you're going to see that I've got RStudio open again. Again, we've got our script editor here, our console, our environment, and where our plots are going to go. And we're going to walk through how to download and look at sea level. So this is going to be sea level part 1. So one of the things that we may look at here is what the sea level trend is. Is it going up? Is it going down? Is it accelerating? Is it getting faster? And so one of the places where you can look at that data is here at climate.nasa.gov/vital signs/sea levels. We're going to go ahead and copy that, and we're going to put that right back in here just as a data source for us. And let's go back over to this. And when we go there, we can scroll down and we can see satellite data for sea level from 1993 to present. And this is the trace. So this is the sea height variation or change since 1993. And you can see it's been going up. It's got some ups and downs. And the rate of change, or how many millimeters it changes per year on average, is right now something like 3.2. Overall, it's gone up about 88 millimeters, which is about 8 centimeters, 8.8 centimeters since 1993. So we're going to think about this curve here in just a minute. And one of the questions that comes up is whether or not this curve is increasing linearly, like is this rate the same, or is it actually getting faster with time? To do that, I'm going to drag this out of the way. Let's ask some basic questions about what does it mean to have sea level increase or sea level increase and accelerate. Okay, so what does that mean? We're going to need to have some time dimension. Let's just make up an example here of time. And we're going to have a time vector of 1 to 100. This is just arbitrary units of time. And let's think about maybe a car, how far a car is traveling. We can say is, let's just make it equal to time. And so what does that look like? Well, we can run these in here. Remember our little run button. So we've got time and distance, and if we plot time and distance, so this is our x value, this is our y value here, we're going to get a plot. That's just a one-to-one line. And so what does this mean? After 20 units of time, say 20 hours, we've gone a distance of 20. Let's call it 20 miles, 20 miles. So if I've gone, in 20 hours, I've gone 20 miles, that means that the car is traveling at 1 mile per hour. So every hour that goes by here, we go 1 more mile. Okay, we can come back up here and say, well, what happens if there's some kind of offset? We don't start at 0 with our car, we start at 100. This is what's called having an intercept. So let's go ahead and plot this. And what do we get now? Well, we're starting at distance 100, and at time 120 we've traveled to marker 120, and since we started at 100 and we ended up at 120, the difference between these is 20. In 20 hours, we're still traveling at 1 mile per hour. Okay, so let's come back up here. Let's change this intercept to 0, and now let's increase the speed of the car. Let's now say that the distance is going to be time times, say, 20. So what does this mean? This means that for every time period, we're going to go 20 times the time period. So when we run this, We say, oh, after 20 time periods or 20 hours, we have gone 500 miles. That means we're going at 20 miles per hour. So this little thing here is the rate. This coefficient in front of the time variable, that's a rate. This is how fast you're going. So how much distance you're going per time. Okay. Now, just having a line like this, just like we had like a sea level or anything, we can estimate that rate using what's called a linear model. So let me just give you a linear model example. And here's the conundrum, or here's the question. Up here, we created our data, right? We said this was time, this was going to be our distance, so our x value is our time, and our y value is our distance. There is a function called LM, which will estimate our rate of change. Now we know what it is to begin with, 20, but what this LM does, let's just do question mark LM, is fitting a linear model. And what that means is that we give this model or this function data and we ask it to estimate two things, our rate of change and our intercept. So let's give this a try. It's probably best if I just show you what this means and you'll get a sense for it. The linear model wants the response variable first. So here's our x variable, here's our y variable, so our distance is responding to our time. We're going to do a linear model of distance is a function of time. That's what this little squiggly means here. That's what that's the squiggly. And we're going to call this thing the linear model equals this thing. And so if I run this and then type summary of lin mod, we're going to get a table. Okay, this is a statistical table, and there's lots of different numbers in here, but here's the thing you got to know. We want to know what the estimate is for our intercept. It's a really, really small number, negative 5.45 times e to the minus 13. So there's 13 zeros in front of this, so it's essentially 0, which is what this is here. Our time is 2.0 times 10 to the 1. So whenever you see like an e to the 1, you just move the decimal place over one time, and so our time, or our rate of change with time, is 20, which is exactly what we put in here. Okay? All right. So we estimated that. You say big deal, right? So we estimated the data, we knew exactly that we put into it, but we're going to use this in just a minute. The other thing we're going to do here is run a prediction. So let's go ahead and we're going to make an object called predict the linear model, and that's going to be, I want you to predict the y values, the distance values in lin mod, in our linear model. So give me the y values out of this linear model. Okay, so our pred lin model, you'll see, is a series of values that we put out, and we can lay that right on time, or right on top of this plot, using the lines function. Time pred lin model. Let's do the color equals red. All right, we're going to throw that right on top. Oh, pred lin mod not found. Whoops. There we go. Model. All right, so here we put a red line right on top of our dots here. So what was the order of operations here? We made up some data, some time, and some distance that our car was traveling, and we plotted those two things. That were these dots here, these circles. We fit a linear model to it, and then we asked R to predict what our y values would be based on that linear model, and we put that prediction in red on top of this, and you can see it's a near perfect fit. Okay, so far so good. Now, what happens if now we have an accelerating rate of change? What happens then? Okay, well, or sometimes this is called a quadratic model. All right, let me give you an example of that. So just like we had time and distance here, right, we're going to do the same thing. We're going to add a factor here, not just time 1 to 100, but we're going to call it time underscore 2, which is going to equal time squared. So we're going to have a squared function. We're going to have a linear function this time part, and then we're going to compute distance now based on time underscore squared plus 20 time plus 0. So our distance now is going to have this squared function of time in it, just like this. And you'll see what I mean here in just a minute. We'll run this, and now we will plot time and distance. And what you'll see here now is that as time increases, we don't have a constant rate of change, but we're getting faster and faster and faster as we accelerate. We're going farther and farther and farther. So we can ask the same kind of question. Let's now produce another linear model. Let's fit a linear model of distance versus time. We're going to get an estimate, which are different than before. This is our intercept and this is our time. They're highly significant. And then what we're going to do is try and predict this model. And do the same thing here that we did, and we're just going to copy and paste it. We're going to try and predict this linear model. Now here we're just using distance and time, and you'll see that our red line is not a very good fit. So it goes up, but the red line does not fit this curve very well. So we need a more complex model than just this model, and than just the linear model here. So we're going to change our terms here. We're going to do our quadratic model is now going to be distance as a function of time squared plus time. That's all we've added. So we just added this accelerating term in here. And you remember, our data looks like this. It's time squared, right? Remember, this is time squared plus time. And we're going to run this, and we're going to estimate the coefficients on these two things. Okay, and if we do a summary of quad mod, you'll see, oh, time 2, the intercept is 0, which is what we had up here. There's 0. Time 2 has a coefficient of 1 in front of it, which is the same as having nothing here. So it's just 1 times time 2. And here's our 20. Here it is. 2.0 times 10 to the 1. So right there. So we have our fit. And so now we can go ahead and do our predict our quadratic model. Predict quad mod. I'm going to predict based on the model that we fit, and we're going to add the lines. I'm going to predict quad model, and we're going to make this blue, and there we go. Look, the blue line is right on our points. So how do we tell which is a better fit? So we had our linear model. We did our summary of our linmod. One estimate you'll see down here is something called an R-squared. It's just how well the data fits, is 0.95. A perfect fit would be 1. But if we do now the summary of our quad mod, you'll see that our R-squared is 1. So it's a perfect fit. So in this case, our model with our squared term in it fits the data perfectly. With just a linear term, it fits it well, but not as good. And so we would conclude that the model with the accelerating term fits our data a little bit better. Okay, so now how are we actually going to use this? How are we going to use this? Well, let's go ahead and load global mean sea level. And we're going to get that, again, from our vital signs. So here's our data that we want to get. And here's what's called an FTP server. We can click on that. And that's going to load this big text file. Big text file here. Let's take a look at it. This is global mean sea level data. This file contains global mean sea level variations computed at the NASA Goddard Space Flight Center under the auspices of the NASA MEASURES program. This GMSL, which is global mean sea level, was generated using the integrated multi-mission ocean altimeter data for climate research. It combines sea surface heights from these different satellites to a common terrestrial reference with all intermission biases, range, and geophysical corrections applied and placed into geo-referenced orbit. This means that this is just what these satellites do is they orbit at the same altitude, and they ping the surface with radar, and they measure how high the sea surface is. So when we get down to the data down here, it gives us a column description. This HDR means header. It gives us a column description of each of one of these things. So column 1 is altimeter type. 2 is the merged file cycle. We're going to ignore those things. 3 is year plus fraction of year. We're going to need that one. So this is like our date stamp. So this is 1993.01. So it looks like it goes from 93 all the way down to 2018. Okay. And then here's the number of observations in each one of those references, what the mean is, and then here are, now starting at 6, these are the global isostatic adjustments, the different sea levels. The one we're going to be working with is 12, the smooth Gaussian day type filter with annual and semi-annual signal removed with respect to 20-year mean. So that's the one we're going to be using for this exercise, but you can use any of them. You can use 6, 8, 9, 11, or 12. Those are sea level records. Now we need to read this data in to our computer, and it's easy to do that since we have, this is on an FTP server. This is just a big text file. We can copy this whole thing, and let's go ahead and just paste it over here. This is where we're going to read our data from. And around that, we can just say, let's do, this is called our NASA global mean sea level equals read.table. Put this thing in quotes. We're going to read that. And if we just try to read this thing, I'm just going to warn you, yeah, it's going to give us an error here. The error is that it doesn't like, it sees that there's all this header information. So we have to skip all of that. So we have to count the number of header lines before we come down to here's our data. See, here it says header end. And I've already done that, and it turns out that we just need to skip 50 lines. So it's going to skip 50 lines and then start reading in data. Okay, now we did that. Let's take a look at the top of this. Let's do a head of NASA GMSL. Head just looks at the top of the data, and you'll see here's column 1, 2, 3, 4, 5, all the way through. You know, does this look right to us? Let's go ahead and see if we've read this incorrectly. Yeah, so here's the first date record is 1993.011 or 012. There it is right there. There's 46462. There it is right there, and then there's our different sea levels. So our year, if we put year in here, is NASA GMSL column 1, 2, 3, the third column. We're going to pull out the year, and now we're going to pull out GMSL, global mean sea level, is NASA GMSL, this big matrix we read in, and this is going to be column 12 I'm going to use. And I said you could use the other ones if you prefer. Here we go. So let's go ahead and run this, and we should be able to plot year and GMSL. This should produce, let's do a line plot, our line weight equal to 3. This should produce our sea level. Look, there it is. And does that look like this one on the NASA site? Let's go ahead and close that. Yeah. Pretty good. All right, so we have this one here and this one here. And one thing you'll notice difference, looks like the same pattern, but look at where the 0 is. Here's 0 is referenced at 2005. And here, 0 is at 1993. Why might that be? Well, that is actually found in the description up here. For this is 2005 0 referenced. And to compute the rates, it doesn't really matter what it is, but our linear model will just estimate a different y-intercept. So in this case, it's 0 referenced. In the online case here, it's referenced at 1993, but they tell you exactly the same information, how fast it's rising. And in this case, it's just telling you how much it's risen since 2005. But we could also compute how much it's risen since 1993, and you'll get the exact same number as you would if you looked at the online graph here. So same data. All right. So here it says it's raised about 88 millimeters. Here we go from about minus 40 to a little more than 40, like 44. You add those two together, you get something like 88 millimeters. Okay, so far so good. Looks like we have the right data. So let's go ahead and fit a linear model to this. So let's do our, let's do this, so linear model for global mean sea level. So we'll call this our global mean sea level linear model. Just like we had before, here's our linear model, our response. Our y value is going to be our GMSL is a function of year. It's a function of year. Okay. Let's go ahead and run that. Okay. And let's take a look at the summary of GMSL lin mod. Just like our previous example, if we run that, we see that our rate of change, which is right here, so how fast it's rising per year, is 3.212 millimeters. So this is in units of millimeters, 3.212 millimeters. And if we go back over to our NASA rate of change, it says 3.2. So we calculated 3.212 millimeters per year. So it looks like we're on the right track. And now, just like before, let's go ahead and do a prediction. prediction of our GMSL linear model. We're going to use the predict function, GMSL lin mod, and then we're going to put the lines on this. Our x value is going to be year, our y value is going to be our prediction from this thing, and our color equal red, line weight equal 2, so we'll go ahead and run these. There we go. That is the linear model, or the linear prediction, at a constant rate of 3.2 millimeters per year. So on average, that's what this model looks like. All right. Let's go ahead and try doing now an accelerating model. For global mean sea level. This is going to be our quadratic. Put in quotes. And you remember what we had to do before? We had to make a year underscore 2 is going to equal year squared. So if we just run that, right? So here's our year that's the year from our from global mean sea level, and year underscore 2 is just going to be the square of that, so gigantic numbers. And let's go ahead and want a quadratic model now. So GMSL quad mod equals our linear model. Our responses are to global mean sea level is now going to be equal to, and I just remind you from up here when we did our quadratic model, where is it here? We just had our response, in this case was our distance, our squared time, and then our time. And that's going to be the same thing here. So what's our squared time? Year 2 is our squared time plus our time. And let's run that. Oh, says it's not a valid model. Oh, I know why. Because that doesn't need to be an equals. That actually needs to be that little tilde sign for this to work. Run that. Okay, there we go. So let's go ahead and predict this. We can just copy this here and modify it. We're going to predict our now quad model. And we're going to add a line to it. Here, this is now going to be our quad model, and let's put it in blue. All right, so the blue represents the fit of a quadratic or accelerating model on there. And let's make this look a little bit nicer here. So let's go ahead and add a legend to this. So we're going to legend to the plot. We're going to put it in the top left of the plot. Legend is going to be, we need a list of things that are going to go in our legend. Global mean sea level in millimeters. And this is also, how do I want to put this? This is a 2005 zero reference. Almost a 2005 reference. Okay. Then the next thing is going to be GMSL linear fit. And the next thing is going to be our GMSL quadratic fit. Line weight is going to be 2. Our color for our different things is going to be black for our mean sea level, whoops, put concatenate in front of this, black, red, blue. I think that's what we need. Let's give that a try. Yeah, there we go. So there's our global mean sea level in millimeters, our GMSL linear fit, and our GMSL quadratic fit. So we might ask the question, which one's a better fit? Well, we can do that. Remember, if we can just do our summary of our GMSL linmod, and let's just take a look at that R squared statistic, 0.9742, pretty good. And summary for our quad model. 0.9837. So a little better, a little bit better, a little bit better. Okay, so it looks like that the quadratic fit fits just a touch better than the other ones, but what are the implications of this? So let's, if we take these two models, remember we could predict them. Let's go ahead and predict mean sea level with our linear and quadratic models. Right? Remember, the quadratic is the accelerating models out to year 2100. All right, so let's make a couple new variables. Our prediction year, this is what we're going to predict over. We're going to predict from 1993 to 2100. And our prediction year underscore 2 is just going to be the square, and we're going to need that for our quadratic model, year squared. Okay. Now, we got to predict with new data. So we have these models that exist, but we want to stick new x values into them. So right now our models know about these x values from 1993 to 2018. We want to stick new values in here from 1993 to 2100 and see where we end up. So let's do that. So GMSL underscore linear model 2100. Okay, let's go ahead and predict using our GMSL lin mod. Remember, these are going to be predictions with zero reference at 2005. Linear model, okay. And we have to add an argument here. The new data that we're adding here, I'm going to give it a list of new X data, or new year data, where our year equals our pred year. Okay, why am I doing that? Let's take a look at this a second. If we remember, look at our linear model here. Our linear model knows about a predictor called year, but we're gonna say that year now is actually our prediction year. So we're going to take whatever is in our prediction year and stick it in here. So our prediction year is that, and we're going to ask for a confidence interval. Interval equals confidence level equals 95% confidence interval with our data. All right, I think this is going to work. So let's go ahead and run that. Okay. And now we got to do the same thing for our quadratic model. So this is our quad model now. This is our quad model now, and now our new data year is going to be our pred predicted year, and our year underscore 2 is now going to be our predicted year underscore 2. So we're just letting the model know that we have new data coming into it that we want to predict out to 2100. Go ahead and run that. And now let's create a plot. Plot. Pred year. Right, there's our prediction year, and GMSL linear model X and Y. Well, let's take a look to see what this is first. These are our predictions. So here's our fit, our first column, our lower and our upper bounds. Those are our two 95% confidence intervals. So we just want the first column. That's our prediction. Our line weight is going to equal 2. Our color, you know what we're going to do here instead? Instead of the linear model, we're going to put the quadratic model on here first, because that's going to have a much larger Y range. Color equals blue. Type equals line. And our X label will be year. That's the year that we're going to go to. Our Y lab is going to be global mean sea level, 2005 reference in millimeters. Okay. There we go. So that's the prediction now from, there's our accelerating model, right? You can see it accelerating up. And now let's compare that to, let's put our confidence intervals on there, shall we? Let's do that. Well, that's pretty easy because we know that we go for our lower than our upper. So if I can just edit this thing, turn this to lines, add some lines. This is going to be our lower bound. Yeah, we don't need the X lab and Y lab anymore. So we already have that on there. And LTY equal 2, that's a dashed line. Okay, there's our confidence interval, that's one. Let's now add another one. This is going to be our upper one now, this is the third column, so there's the upper confidence interval there. Run. Alright, that looks good. And now let's go ahead and add our linear model onto this. Prediction, this is going to be now our linear model. And let's make this red. And we don't need our X lab and Y lab anymore. And this should be lines. I'm going to add a line, a red line. This plot. There it is. So that's the linear projection out to 2100. And we can do the same thing here with the confidence intervals. So just copy these two. And all we have to do is change this to the linear. Everything else stays the same. Change the color. Not everything else, the color changes. And we can copy both of these on. That's the 95% confidence interval. Okay. All right, now let's dump on our actual sea level data. Remember our original data, year, and our GMSL, and our line weight, let's make that a 3. There's the data. So here's the data that we fit, that black area. And remember, we fit 2 models to it. One accelerating, one not accelerating. One just a linear trend, so that would be the red projection out. And here we go. Here is the linear Here's the quadratic accelerating projection. So quite a difference depending on what model you choose to fit your data. So let's go ahead and put a legend on this. Top left. Okay, so we'll do the global mean sea level on there first, and then we'll do our GMSL linear prediction and our GMSL, oops, gotta put quotes around it, GMSL quadratic prediction. And also our 95% confidence interval. Okay. Line weight is going to be 2. Line type is going to be, it's going to be us. We're going to have a solid, solid, solid. 2 is going to be our dash line. That's going to denote these dash lines here. And our color is going to be black, red, blue, black. There it is. So again, here's the data that we fit, right, when we ran our models. Here's the linear prediction of that data, and here is the quadratic prediction of that data, and our 95% confidence intervals for our 2 models. So you can try this with the other sea level measures that are in there, and see if you get anything different. But for now, that's where we're going to leave it. Oh, don't forget to save your code here. Save.